In this video, we are going to explain you on the deadband required for power electronics applications. So in the last video, we have seen the modulating signal whose duty was varying from 0 to 100% and 100% to 0. Now to modulating for deadband generation, we need the complementary pulse to generate the deadband pulse the same. So for initially, we will look at how can we generate the complementary pulse, and later we will include the deadband on that pulse. So to generate the complementary pulse, we have to go to the Composite studio. In the Composite studio, to generate the complementary pulse, we have to go to the setup ePWM1 modules. Okay, so we will go to the ePWM module, and here you can see. Okay, so these are the previous things which we have included in the projects, and this line we are including to generate the complementary pulse. So they are the action qualifier we are using for the B action qualifier for B, and this is the 0x000 the 0x0090 is to generate the complementary pulse. So this action qualifier function you can see on the previous videos. Okay, so how we got this 0x0090. So this action qualifier value you can check on the previous video. So this line will generate the complementary pulse of the same frequency and same magnitude. So we will see with the CRO. As you can see here, this is the modulating waveform, where upper waveform is the normal signal which we have created in last lab, and the down one is the complementary signals. So his pulse width is varying from 0 to 100%, as you can see here. So this is the fixed PWM. If you are zooming this, both signals are complementary with each other, and one is turning on and other one is turning off at the same time. So there is no delay between turning on and turning off of these pulses, and these are complementary in nature. So for examples, this we have voltage source inverters, and this is the DC bus capacitors, and this is the power semiconductor devices. So we have 6 power semiconductor devices in this one, and we are applying the PWM signal between the gate and the emitter of the semiconductor devices. Okay, so one more thing, we cannot turn on both the switches at the same time. If we are turning on both the switches at the same time, it will DC source will get short circuited, and there will flow the huge current in the circuit. So to avoid this, what we are going to do, we are just turning on this one and we are turning off this one. So this switch is, when this switch is turned on, this switch should be turned off, and when this switch is turned off, this switch should be turned on. So these two switches will be turned on and off some complementary fashions. Okay, but the thing is, we cannot turn on and just turn on and turn off at the same time. If we are, this is the ideal conditions, there won't be any effect, but if it's the switch are non-ideal in the nature, so they cause a shoot through problem, so they may get short circuited. So the motivation for the deadband is that when we apply this kind of pulses to the upper switch, and this is the complementary pulses to the lower switch, and we are taking output between these two terminals. Okay, so during this case, what will happen? For example, if we are taking the zoom part of this part, and if we are, one switch is turned on, and this is applying to this portion and this is applying to this portion. So during this condition, one switch is getting turned on, one switch is getting turned off. And if you know the semiconductor devices, and if we see the data sheet, mostly turn on time is much faster than the turn off time. So when this switches will turn on, this switch doesn't completely turn off. So during this case, there is a chance to short circuit this path. When this is getting short circuited, there will be huge current will flow throughout this path. So to avoid this, what we need to get some kind of delay. So when this is turning on, your first switch should completely turn off. So after certain interval of time, so this is the certain interval of time, after some time your upper switch should be turned on. Okay, so this motivate us to use the deadband for the PWM generation. So for doing this, we are using the deadband module from the DSP processor. So deadband will generate deadband will with the help of deadband circuit we are achieving we are out we are protecting our inverter to getting short circuited. So this is the basic block diagram, and this is the basic architecture how the deadband is going to work and how ePWM deadband is going to work. So we have a three set of registers. One is the output mode, another one is the polarity selections, and the other register is the in mode. Okay, so in output mode, when the S1 and S2 sorry S0 and S1 are connected to 0, we are directly connecting the PWM A and B. We are directly connected to the PWM pulses generating from the DSP processor. Okay, so during this case there is no delay in the PWM A and B during rising edge and falling edge. So by selecting the S0, S1, S2, S3, S4 and S5, we are creating the deadband. So how we are creating the deadband? So as you can see from this slide, when we are keeping the S1 and S0 are 0 0, so when S1, S0 and S1 are 0 0, so during this case there is no delay in the output, right? When we are keeping S0 is 1 and S1 is also 1, but the thing is we are keeping S3 is 1, S3 is connected to here and S2 is connected to here, so it is directly connected to this rising edge delay block, and it is directly connected to complementary signals. Okay, so and here we are seeing that S4 and S5 are connected to 0. If these are connected to 0, S2 is connected to 0 and S3 is connected to 1, so will be active high complementary signals, because this is the active high signals and this S3 is connected to 1, so this is the active high complementary signals. So how the signals we are getting here? So this is our original signal. Okay, so yeah, this is the rising edge delay. Okay, when so it will provide some kind of rising edge delay, and this is the falling edge delay. So there is no delay at the initial, but when your signal is getting turned off, so it is not turning off at the same time, it is after some delay it is getting turning off. So this is the falling edge delay. Then active high complementary, so when your signal is high, okay, so when your signal is high, in this case it will provide some kind of delay, but the complementary signal won't provide the delay when the complementary signal is going to high. Okay, this point it is going to low, but complementary signal should going to high here, but after some time, because this is the active high complementary, so it is providing the delay when your pulses is going to rise. So it provide the active high complementary pulse. Similarly, by selecting the values of uh, output mode and the polarity selections, we can make like what kind of actions we want. We want active high complementary, active low complementary, active high, active low, and we don't want any delay, and we want the delay in ePWM XA with the falling edge delay, and we want the delay in ePWM A with the rising edge delay. And if we are keeping the output mode is 1 0, and S2 and S1 S3 can be 0 1 and 0 1, so with this we don't know the output which we are getting, there will be no delay. So by selecting this this S0, S1, S2, S3, S4 and S5, we are creating the delay at different location, different PWM pulse we are getting. So this is the active high complementary, this is the active low complementary, this is the active high, and this is the active low. So depending upon our requirement how we want to provide the delay, so this is done by the deadband. So these are the different operations. So some of them are useful which we are going to use in our experiments. So we are not using all the possible combinations, there will be several possible combinations, but we are using some of them, or we are not going to use all of them. So depending upon requirement you can select any one of the combination possible combination. So what kind of registers? So now we want to provide the delay, okay, during the falling edge and rising edge. Okay, So how much delay we want to provide? The first thing we need to think about how much delay we want to provide. So the delay you can check with the data sheet, whatever IGBT and MOSFET you are using. You can check with the data sheet, and with the data sheet you can check the what is the falling time and what is the rise time. So with the help of that you can select what is the how much delay you want to provide. So if you want the delay, so what kind of resistors we need the deadband rising edge delay, deadband falling edge delay. Okay, so how to calculate these values? So if we know our time based clock is 150 megahertz clock frequency, and our rising edge delay is suppose you want to a 10 microsecond delay during the rising edge. Okay, so this is your pulse, and but you want to turn on after 10 microseconds. So this is time delay you want. So for this case you are getting the deadband rising edge delay will be equals to 1500. Okay, similarly if you want the falling edge delay, so deadband falling edge delay will be 1500. So in this case you are getting the 10 microsecond delay here, and a 10 microsecond delay during the falling edge conditions. Okay, so you are getting total 20 microsecond delay. So we'll see with examples, no issue. And now you have a delay, right? Now you have given the delay, how much delay you want, but at what point you want to give delay, like you want active high complementary, active low complementary. So depending upon the polarity selections, like depending upon the input mode as given here, you can check the what is the output mode and what is the polarity selection. Depending upon the input mode you can select at what point what kind of pulse you want at the output side. So in this case these are the ePWM deadband control registers. So your output mode, depending upon the output mode and polarity selection and input mode, we can select at which point we want to get our PWM pulses. So depending upon this these architectures you can select what kind of pulses we want, and with the help of this diagram you can get what kind of pulse you want and where you want the deadband, actual deadband. So depending upon your specifications of your inverter specifications, you can select these values accordingly. So now we will come to now what we'll do, we'll just do the delay time for the rising edge on the pair of complementary signals, and we are doing the active high complementary, and input signal to the deadband unit is ePWM1A, and the deadband will generate the ePWM1A and ePWM1B. So what kind of registers need? We need the deadband rising edge delay, deadband falling edge delay, and deadband control registers. Okay. So to continue with the previous slide, we will come to the Core Composite Studio. Here you can see we have to add the additional line of code with the same PWM which we have generated in the previous few minutes back. So here we need some kind of code to generate the deadband units. So what we need to add with this one, as you can see here, so we need to add the deadband falling edge delay and deadband rising edge delay. Okay, so we will uncomment this part. Okay, so we are doing this for the ePWM1 registers. We are giving the delay between the complementary signals generated at ePWM1. So this is the deadband registers. Its value is we have taken for 10 microseconds is 750 because we have divided the clock by 2. So this time your time based clock will be 75 megahertz. Okay, so with respect to that we got the deadband and rise deadband delay dB FED and dB RED is 750. So now with the help of previous few minutes back we have gone through the polarity selection in mode and output mode. So output mode we have selected is 3, and in mode we have selected is 0, and polarity selected we have selected is 2. So depending upon these two values we can provide the delay and what point of times we want to provide the delay. So we are taking the XT high complementary signals, and initial value we have taken for the TVPRD is 37,500, and the compare registers we have taken is 12,500 as compared values, as we have already discussed in the few minutes back. So Now we will run this and we will see how our pulse will look like. So as you can see here, if we are zooming the pulse, we can see we are getting the delay between the two complementary pulse, that is the 10 microsecond. This because the time scale is 10 microseconds. So between the rising edge and falling edge, we are getting the 10 microsecond delay. And if we are shifting this pulse to the more right, so we can see there also we have a delay of 10 microsecond. Okay, this is not, so we are scaling this in the left side, we are shifting the pulse in the left side with this, and we'll see. So you can see here also we have a 10 microsecond delay time. So we have a total 20 microsecond delay time between the initial of the pulse and the final of the pulse. So these two pulses are complementary and we have a 20 microsecond delay time. So now we will again change to 10 microsecond to 5 microseconds. So we need to change the deadband falling edge delay and deadband rising edge delay. So we have to keep it is as 375 and 375 under deadband falling edge delay and deadband rising edge delay. Only these two values we have to change the delay. Now we will run it again and we will see what happened in the pulse. So we will run it. So you can see here now the pulse width is changed, like delay length has been changed from 10 microseconds to 5 microseconds as we changed the deadband rising edge delay and deadband falling edge delay. So this is 5 microsecond. Now we will shift this pulse to the right and we will see. So here also you can see we have the deadband delay is the 5 microseconds, as you can see. Okay, so this is sufficient to trigger your IGBT and MOSFET. This delay is sufficient to trigger 10 microsecond is sufficient to trigger your IGBT and MOSFET. Okay, so if you have any query regarding this, you can contact me on a comment section, and don't forget to like, share and subscribe my channel. Thank you very much.